Hello, my name is Andrea Arauza Rivera. I'm an assistant professor at Cal State East Bay, and today I'm going to talk to you a little bit about fractal geometry. So let's get started. So this is just an outline of what I'm going to talk about in the talk. So I'm going to start with just some fundamentals about fractal geometry, and really starting with this example of the coastline of Britain. I'm going to use that to motivate the idea of fractal dimension, which is one of the big tools that we use in fractal geometry. After that, I'm going to talk about some of the frontiers in fractal geometry. So I'll talk a little bit about my work in an area called non-commutative fractal geometry and how it might be used to solve some problems from analysis on fractals. And then at the very end, I'm going to talk a little bit about how we might use some of the tools from fractal geometry to help in the analysis of data. So let's get started. So first here, like I said, I'm going to just sort of motivate some of the fundamental ideas from fractal geometry. And one of the nice first examples to think about is this idea of the coastline of Britain. So here in gray, you see an outline of Britain with the coastline here and its jaggedness over on the sides there. And the idea is really, how do we measure the length of the coastline of Britain? Okay. So if you think about this, right, you think about, okay, how would I do it if this was, like a problem that I had to solve? I'm some sort of engineer, right? And I really want to know the length of the coastline of Britain. So one thing you might do is try to discretize the problem, right? So get yourself a very large tape measure or some sort of ruler, right? And just go to town, right? Start at some point on the coastline of Britain, take your tape measure, however long it might be, and stretch it out to the next point that you can reach, the furthest point you can reach that's still on the coastline. And then start again, right? Maybe stretch out your ruler again, and then again, and then again, and then again. And in this very discrete way, get an approximation for the length of the coastline. Yeah. So I have this little table that sort of tells us what some of the measurements would be. So if I used a ruler length or a tape measure of length 500 kilometers, right? So maybe these little line segments are each 500 kilometers. And I added up the lengths that I get when I place those rulers along the coast, I would get something like this, right? 2,600 kilometers. I could do it again, right? Maybe one thing you can tell here is that I'm missing these little pieces in here, right? So there are some intricacies, some pieces of the coast that I can't quite get to with a ruler length of this size. So maybe I see that I can get a better approximation if I just use a smaller ruler, right? Something a little shorter. So maybe I do something like this here. Okay. So for different ruler lengths here in my table, I've got what the length would be, right? What my approximation for the coastline length would be. So for a ruler length of 100 kilometers, I would get this 3,800 number. For 54 kilometers, I would get 5,770. And so on here. You can see I put in the differences here. So this 1,200, that's the difference between these two numbers. This 1970 is the difference here, right? And so on here. So you might be able to notice that the length of the coastline, my approximation, is getting bigger at each time, at each point, right? As I use a ruler that gets smaller and smaller, my approximation for the length gets bigger and bigger. And the differences here, this is maybe a little more startling, the differences are also getting really, really big. Okay. So what this is an example of is what we call a non-rectifiable curve, right? This is a curve where if we try to measure its length and we try to approximate it with these smaller and smaller rulers, we get something that diverges, right? We can't get like a nice finite number. We just get infinity. Okay. So just to build a little bit of contrast here, we looked at the coastline of Britain. Let's look at a nicer shape, right? Let's do the same thing, same exercise. So try to figure out, the length of the boundary here, but with a nicer shape. So for example, we might use a circle, right? And think about how do we approximate the circumference of this circle? Okay. So we have very nice formulas for the circumference of a circle, but let's say we didn't have those and we just wanted to do some approximating. So one thing I might do is I might take some of my ruler lengths, right, and draw some line segments like this, and maybe use this as one of my approximations for the circumference of the circle, right? So once again, I'm sort of discretizing the problem. Instead of doing something like this, I'm using a straight ruler, right? And we're pretending that all of these line segments are of the same length here. But I'm sort of starting at one place, putting my ruler down as far as it can go, but still on the boundary of my circle there, and then putting another ruler down, and so on until get all the way around the circle. So let's say, just for the sake of having something concrete here, that my circle has diameter of 100 kilometers. So then if I used ruler lengths of these sizes to try to estimate the circumference of this circle, I would get these estimates for the length of the circle. Really, I should say circumference of the circle. And one difference you can see between this and the previous example with the coastline is that here I'm really starting to converge upon a number, right? And you might be able to guess what these digits are starting to resemble. Yeah. But the main thing here is that this length, it's not going to blow up, right? It's going to converge onto a number. It's going to steady out. There's not going to be a lot of change as I let my ruler size get smaller and smaller. And it's going to converge to the circumference of the circle. And that really shows one of the big differences between something like a circle, a nice smooth shape, and something like the coastline of Britain, which has more fractal properties. Okay. So what does this tell us, right? What did this comparison tell us? Well, for example, one thing is that it shows us a significant difference between the geometry of the coastline of Britain and the geometry of the circle, right? We can see very different things happening. Fractal geometry is really the embracing of these strange examples that have these fractal properties, right? I think for a long time, people sort of ignored these examples, these sets with some strange properties. They just ignored them as, you know, some pathological counterexample to a nice theorem that just, you know, causes trouble. But really, fractal geometry leans into that chaos and really thinks about how do we quantify some of these fractal properties that we're seeing. Yeah. So we build many tools to try to study these sort of differences between something like a circle and something like a very rough coastline. And one of the tools that we have in fractal geometry is the idea of fractal dimension. Okay. So I'm going to tell you a little bit about fractal dimension. So just to motivate things here, maybe I'll give you a little bit of a chance to write some stuff in. So if you'd like to listen to the instructions here and then take a second and pause the video, and then you can fill some things in for yourself. So here I have a table. I've got some dimensions that we maybe feel a little bit comfortable with. So 0 dimension, 1, 2, and 3. I won't go any further than that because it gets hard to draw those shapes. But take a second and think about, can you come up with a set that lives in each of these dimensions? So for example, if I asked you to draw for me a one-dimensional shape, what sort of shape would you draw, right? Same thing with 2 dimensions, right? If I asked you, what is your favorite 2-dimensional shape? I'm sure you have one. What would you draw, right? So go ahead and draw those in for me. And then think about whatever shape that is, right? So your favorite 1-dimensional shape, whatever shape that is, how do you measure its size, right? So if I asked you, how big is that set? Give me some number that tells me how big it is. What are you doing, right, to find that number? What sort of measurement are you doing? Okay, so go ahead and pause the video, fill that in. Okay, so now we'll fill it in together. So for 0 dimensions, maybe this is one where if you haven't quite thought about this idea, then it's sort of hard to come up with, but here is what you might draw. So for 0 dimensions, you might draw something like just a set of points. Okay, so here, for example, I drew 5 points. Okay. In dimension 1, you might think, well, what about something like this, right? Just a little line segment, or you know, a 1-dimensional little curve. For dimension 2, you might have something like a square with some of it filled in there, right? Some sort of plane. And in dimension 3, you might have something like a little cube. Okay, so something like that maybe. Yeah, so something like a little cube, right? We live in dimension 3. And like I said, for the remaining ones, so 4, 5, and 6, right? They gets a little hard to draw, but you sort of get the idea here, right? These are some sets that live in these dimensions. If we think about how do I measure the size of sets that live in this dimension, it sort of changes as we go up the scale here. So at the beginning here, if I asked you to tell me a number, right? What's a number that you would tell me for the size of this set? One thing that's very natural to do is to just count the number of dots that I drew on there. So for this set in particular, you might say, well, 5, right? The size of that set is 5, because really all you did was just count the number of points. Okay? So in dimension 0, the ideal way of measuring the size of a set is really by counting. In dimension 1, you might think about the idea of measuring length. So maybe I have a piece of string, I put it down onto that curve, and then I take my piece of string and flatten it out along the some sort of ruler, right? And then I have a measurement for how long that that little segment is. Okay? So there, I'm really using this idea of length. For dimension 2, I might think about area, right? What is the area of this little square region here? And for dimension 3, I might think about volume. So the ideas of dimension and the ideas of measure are very deeply tied together. One of the reasons that a set like this lives in dimension 1 is because when I measure its length, I get a meaningful number. Meaningful in the sense that if, for example, I counted the number of points on this set, so maybe I measure this set with counting. If I count, I'm going to get, so I have uncountably infinitely many points on this curve, right? So I really can't even count it. So I get infinity, right, if I try to count the number of points here. And that's not really very meaningful, right? It's too big to be counted. Another thing you might think to do is, well, maybe I look at its area, right? And we really don't think about area for a set like this because it's got area 0. So once again, we don't get anything meaningful, right? It's too small to have any area. So it's too small to really be thought of with dimension 2. So the ideal way of measuring this set isn't with counting or with area. The ideal way is to think about its length because we get something meaningful, right? Maybe this is, 2 inches on my screen here. Okay. And similarly for these other sets, right? This way of measuring is really the way of measuring that's going to give you something meaningful. And that's part of the reason why these sets live in these dimensions. Yeah. So one thing you might notice is that here I drew a lot of very nice sets, right? They don't really have fractal properties. So let me show you an example of a set that is fractal, and then we can think about what dimension would it live in and sort of see, we can take a look at what happens when we try to measure it with some of these measures. Yeah. So I'm going to share with you one of my favorite fractal sets, which is the Sierpinski gasket. So that's this set right here. I'll describe to you 2 different ways that we build the Sierpinski gasket. Both of these are going to be helpful. So I'll use these 2 images to help us understand how to build the Sierpinski gasket. Okay. So one way you can do it is by using these little triangles up here. So in both of these cases, I'm going to start with an equilateral triangle of side lengths 1. In this first construction, I start with an equilateral triangle that's fully filled in. To get the next step, so a lot of times we build these fractals in steps here, so in different stages. To get the next step, I'm going to put a dot in the middle of each of these edges here. Okay. I put a dot there and then connect those line segments and remove the area that they enclose, right? So that's how we get this set here. For the next step, I'm going to do the same thing, but now with each of these little triangles. Okay, so for example, I'll zoom in on this top triangle. Now, for each of these line segments, I'm going to plop a point right in the middle of them. I'm going to connect each of those points, and I'm going to delete the area that they enclose, right? That triangle encloses. So that's how I get this part of the triangle. And I repeat the same process for this one and this one. In the next step, I do the same thing, right? Now I have this little triangle, right? I've got 9 of these little black triangles. I repeat the construction for each one. Okay, so in this way, I get this sort of iterative way of building up to the Sierpinski gasket. I keep doing this over and over forever. And what I end up with is this set right here, right? The set called the Sierpinski gasket. So that's one way of building the Sierpinski gasket. Another way is constructing it out of an increasing sequence of graphs. So here you can think maybe these vertices, these points here are your vertices, and then these are your edges. So once again, you start with an equilateral triangle of side length 1. This time the area isn't filled in, it's truly just these little line segments, and we're just going to add line segments as we go along here in the different stages. So for the next stage, we take each of these edges, we plop a point in the middle of each of those, connect them with a triangle, and add those edges to our graph, right? So we add these edges. This gives me a new graph like this. I do the same thing, right? So now for this triangle, this triangle, this triangle, I plop a dot in each of the midpoints, I connect them with a triangle, and then I add those edges into my shape, right? So my set. And I do that for each one of these triangles. Okay. So again, I iterate this process, I do it over and over and over again, and I get something that looks like the Sierpinski gasket. So there are some nice theorems from fractal geometry that say that when you do this construction, you get the same thing, right? When I iterate this process over and over, when I iterate this process over and over, I get this same shape, right? The Sierpinski gasket. So these are two different ways of building this space. So let's think about how this space relates to the discussion we were having about dimension, right? So one thing we can do to try to figure out, well, what dimension does this set live in, is we can think about measuring it, right? With the measure that goes with the different dimensions. So we might think about counting, right? So maybe we count the number of points on the Sierpinski gasket. You can maybe quickly see that this is an uncountable set, so we're going to get infinity if we try to count it. So that's not really giving us anything informative. So let's jump up to length, right? So maybe when I think about the length, right? So when I think of it in this way as these little graphs here, so maybe I can add up these lengths and maybe, just maybe, we get some finite number, right? And then it's got positive length, right? Positive finite length. So maybe we get that, right? So we'll do the calculation in a second. Okay. And then, so depending on what we get for length, we can also think about its area, right? What area might I get if I think about the area of the Sierpinski gasket? So for that, this construction would actually be helpful. Okay. But let's go ahead and think about its length first and think about this construction. Okay. So let's see, length, right? So let's measure the Sierpinski gasket, and first let's measure it with length. Okay. So this is helpful because I can essentially just add up the lengths of these little graphs. Okay. So like we said, we start with an equilateral triangle where the side lengths have length 1. So this first graph right here gives me 3 lengths of length 1. In the next step, I add these 3 little line segments. Each of those has length 1/2. So remember, I got these line segments by just cutting these lines in the middle here and then plopping down this little triangle. So I get plus 3 lengths of length 1/2. Okay. Then for each one of these triangles, I add in 3 little edges. Each of those edges has length 1/4. Okay, so I'm adding 9 lengths of length 1/4. So we'll put that down, plus 9 times 1/4. In the next step, you might see what can happen here. So I get 27 lengths of length 1/8, and so on, right? Dot, dot, dot. Okay, so here I would have 27 additional little lines here, and those little lines each have length 1/8. Okay. So we sort of look at this and we start seeing a pattern here, so we get excited about the pattern. Okay, so we have this 3 here that I'm just gonna let hang out of there. And then I can find a nice closed form for this sum. So I can write this as the sum from I equals 1 to infinity of 3 to the I, 1/2 to the I. Just to rewrite this sum a little bit, I'm going to put that 3 to the I in with the 1/2. So this is 3/2 to the I. Okay. So we're excited on the one hand because we have a nice closed form for this length, but we also get a little bit sad because this thing is going to diverge, right? It gets really, really big. Okay. And you might think about for a second here, why does this diverge, right? Why do I know this is infinite? Okay. But indeed, this is infinite, right? This sum is infinite. So when I try to take a look at the length of the Sierpinski gasket, I get infinity, right? So it's too big to be measured with length. So now the next bit I'm going to leave as an exercise for you. So I'll leave it as an exercise for you to show that the area of the Sierpinski gasket is 0. Okay, so if we tried to measure its area, we would get 0. Okay? And I'll just give you a hint, which is to use this construction, right? So using this construction, can you justify why the area of the Sierpinski gasket is 0? Okay? In summary here, we have that the length of the Sierpinski gasket is infinite and the area of the Sierpinski gasket is 0. So what that's telling us is that if I try to think about the Sierpinski gasket living in dimension 1, it's too big, right? I get infinity when I measure its length. So it's in some sense too big to live in dimension 1. When I think of it instead in dimension 2, now it's too small, right? Its area is 0, so it's too small to live in dimension 2. So in some sense, I really want to say that it lives somewhere between dimension 1 and 2. And indeed it does. So the dimension of the Sierpinski gasket, I'll call it D, is given by log base 3 over log base 2. Okay? And this is indeed a number between 1 and 2. And so I'm going to show you where this number comes from. Okay, but this is the fractal dimension of the Sierpinski gasket. Okay, so I'm going to show you now where these terms come from, right? So maybe where does the 3 and the 2 come from? Where do those come from? And then how do we get these logs, right? Where do these logs come from? And so that'll be the next bit here. So where does this value D come from? So I'm going to use a couple of nice sets to sort of start seeing a pattern here. Okay. So I have this table on the side. I've got some scale by numbers. So we're going to take our nice shapes here and scale them by 1/2, 1/3, 1/6. And then we're going to take a look at what is the change in its size, where maybe size here, I'm going to put some quotes around the word size. Okay, so by size, I mean length for a one-dimensional shape like this, area for something like this, and volume for something like this. Okay. So if we take a look at, okay, what happens when I take my line segment and I scale it by 1/2? Okay, so maybe I scale by 1/2, right? So that would be like this part of the little line segment. Okay, maybe I'll scribble it in so it's a little clearer to see. So when I scale my line segment by 1/2, the change in its size is also 1/2, right? So I get 1/2 the length that I had for the original. If I scale by 1/3 instead, I get something similar. So I get maybe this piece right here. Now I've scaled by 1/3 and my change in size is also 1/3. A similar sort of thing happens when I scale by 1/6. So maybe I divide up my line segment into 6ths and I just look at one part of it. That has also changed in size, and its change is a change of 1/6. Okay, so this is 1/6 the length of the original set. Okay. So nothing too crazy happens here in dimension 1, but let's take a look at what happens when we scale something like a square or a cube. There, I think we see something a little bit more clear. We sort of see the relationship here. So for a square, when we scale this, we're essentially taking, putting our fingers on these two little vertices and then just shrinking it down so that it's 1/2 of the scale, right? We're scaling it by 1/2 in all directions. So what that essentially means is that instead of using this full length here, I'm going to use 1/2 of this length. Okay? So I really am getting a little cube, or not a cube, but a little square of size of this size here, right? Somewhere right here. So this is what I get when I scale by 1/2. And you might be able to see that the change in size overall, so the change in area, is really that now I have 1/4 of the area that I had originally. And so now my change in size has been 1/4. If I do the same thing instead scaling by a third, I get maybe a small square like this. And now, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now I have 1/9 of the area that I had originally. So this would be 1/9. Okay. And finally, let's take a look at what happens with the cube. Okay. So with the cube, I'm going to cut this in half, cut this in half, and essentially the depth as well, I'm cutting into half as well. So I've got a little cube in here. Okay, and really I have another one behind it, right? So I've got to, maybe I'll draw the other one just for the sake of the picture here. So I have 4 little cubes down here at the bottom, and then another 4 cubes at the top there. Okay. So when I scaled my cube by 1/2, my change in volume, now I have 1/8 of the volume that I had originally. Okay, so this is 1/8. And you might imagine what happens when I scale by 1/3. I'm going to get 1/27 of the volume of the original. Okay. So let me rewrite a couple of these. So this one here, 1/2, my change in size was 1/4. This is really 1/2 to the second. My 1/9, that's when I scaled by a third. This is really 1/3 to the second. This 1/8 came from scaling the cube by a half. This is 1/2 to the third, and my 1/27 is 1/3 to the third. Okay. So one thing I want to highlight here is that I have some secret, some hidden ones here. Okay, I've got some 2s here for my square, and I've got some 3s here for my cube. Okay. And you might see how those relate to the dimensions of each of these shapes. So let's use this same idea, right? We'll write down a relationship between my scale by number and this an analog for this change in size. And then we'll take a look at, can we use this same pattern, this same connection between these two quantities to look at the Sierpinski gasket. Okay, so instead of thinking about my scale by number, let's think about this as a ruler size, right? So maybe now I've got this 2-dimensional little ruler that looks like a little square like this. And so one change I'm going to make to what the entries in this table is I'm really going to look at the reciprocal of each of these numbers. So instead of thinking about this as being 1/4 of the area of the original square, I'm instead of going to think that I need 4 of these little squares to fill in the original shape. Okay, so essentially I'm just reciprocating all of these quantities here. So that's the number of these rulers, right? These little smaller scaled shapes, the number of these that I need to create the original. So for these scale by numbers, I'm going to call this delta. Okay, so this is like my 1/2, my 1/3, my 1/6. And the number of these scaled copies of the set that I need to create the original, let's call this n of delta. Okay, so it's going to depend on delta. So one thing we might do at the beginning here is to derive a relationship between these two numbers. Okay, and we can use one of these up here to see what we might get here. So for example, for the cube, when it was scaled by 1/2, we saw that scaling this by 1/2 meant that we needed now, so 1, 2, 3, 4, 5, 6, 7, 8 cubes to cover the original shape. Okay, so my delta might be 1/2. And in that case, my n of delta would be 8. Okay, so if I take my cube and I scale it by 1/2, I'm going to need 8 copies of that scaled version to fill up the original cube. Okay. So if I take a look at what is the relationship between my n delta and my delta itself, one thing I can see is this is the same as my delta reciprocated to the power of the dimension of the set. Okay, So think of this as 8 is the same as the reciprocal of delta, which would be 2, to the power of the dimension of the shape, right? The cube. So in this case, the cube is 3-dimensional. Okay, so that's what this relationship is telling me, right? N delta is the same as the reciprocal of delta to the power of d, the dimension of the shape. Okay, and if we looked at this for any one of these other examples, we would see the same exact relationship. Okay, so using this equation here, we can solve it for d. So we can take some logs. So this is where you can see these logs coming up. So if I take log of both sides, right, I get something like this. That d comes forward, so I get log of delta minus 1 here. And if I just solve for this d, I get log n delta over log of delta with a little minus 1 in there. And so I get something like this. So let's think about what happens when I do this delta n delta calculation for something like the Sierpinski gasket. Okay, so let's see where that log 3 over log 2 came from. So if we take our Sierpinski gasket, which originally has this length of size 1, and we scale it by 1/2, okay, scaled here. So we get a copy that sort of looks like this. And if I think about with this 1/2 scaled copy, how many of these copies do I need to create the original? I can see I need 1 to fill in this part, another copy to fill in this part, and another copy to fill in this part, right? So I need 3 copies of this scaled version, this 1/2 scaled version, okay? So my D here is, okay, so my scale here was 1/2. So the reciprocal of 1/2 is going to give me my log of 2 part in the bottom here. And then this n delta is how many copies of that scaled version did I need to fill up the original? And we just counted them and we said that was 3. So I end up with this same expression that I showed you at the beginning here, right? So log 3 over log 2 is the fractal dimension of the Sierpinski gasket. So let me give you the more formal definition now of what this dimension D is. Okay. So this is what we call the box counting dimension. Okay. So for a subset of, and this should really be Rn, this is more general than just R. So for a bounded subset, a bounded non-empty subset of Rn, we can define the box counting dimension in this way. Okay. So we have some scale delta greater than 0. We let n delta of f be the smallest number of cubes of size delta that cover f. So this is an analog for, you scale your set, how many copies of that do you need to create the original? So this is an analog for that. We look at this quantity, the log of n delta of f over log of delta, where here instead of the reciprocal of delta, we just turned that exponent into this minus sign up here. And in order to get all of the intricacies that fractal shapes can often have, we're going to need this delta to be able to get smaller and smaller and smaller. Okay, so that's really because we want to get all of the fine scale information that we have within a fractal set. Okay, so as this delta gets smaller, I get this notion of dimension. Okay, so this is my box counting dimension. And of course, there's always this caveat that the limit has to exist. But if the limit doesn't exist, we don't just give up there. Instead of using the limit, we can replace it with the lim sup. And then we have, instead of the box counting dimension, we have something that we call the upper box dimension. Okay, so just because this limit doesn't exist doesn't mean we throw it all out. We can still use the lim sup. Okay, and that'll always be defined. So this is what we call the box counting dimension. And in fractal geometry, we have many notions of dimension. There's also something called the Hausdorff dimension. There's all sorts of different kinds of ways of defining a notion of dimension. Often many of them are equal to each other. They give you the same thing for some of the nicer fractal shapes, but often they give you something different. Okay. So I'll share with you some of the nice properties that these box counting dimensions have. So one of the reasons that this one in particular, this box counting dimension is nice, is because it gives us a way of approximating the fractal dimension of a shape. Okay. So for each delta gives you an approximation for this limit. So it inherently gives you a way of approximating the dimension just within the definition itself. For nice sets, so something like a line or a square or a cube, this dimension gives you the same thing that you would usually expect. So 1 for a line, 2 for a square, 3 for a cube. So I started this section by talking about the coastline of Britain. So if you're curious, the box counting dimension of the coastline of Britain is somewhere around 1.25. And for reference, here's a fractal shape called the von Koch curve. And this one has box counting dimension log 4 over log 3, and that's approximately 1.26. Okay, so in some ways, the jaggedness, the intricacies, the infinite jaggedness that this shape has is sort of similar to the coastline of Britain, right? This infinitely jagged sort of shape. Okay, so up next, I'm going to talk about some of the frontiers in fractal geometry. Specifically, I'll talk a little bit about some of the things that I've done in the past, and then some of the things that I'd like to do in the future. So first, a little bit about non-commutative fractal geometry. So essentially, this stems from the field of non-commutative geometry without the fractal part. And that really comes from this observation that we have a duality between the category of compact Hausdorff topological spaces and the category of commutative unital C-star algebras. So there's a way for me to translate back and forth between these two categories. So for example, if I have some problem about topological spaces, one thing I can do to either use different tools or gain a different sort of perspective is take that problem and translate it into a problem about C-star algebras. And then I have a new perspective, a new set of tools to try to attack the problem. Okay. So in doing this, what you end up having is this way of thinking about topological properties, geometric properties, in terms of properties of C-star algebras, right? So operator algebraic sort of properties. And what you can do is then lift this requirement of commutativity and think about C-star algebras more generally. So now allowing for the non-commutative C-star algebras and still using those operator algebraic formulations of these topological tools. So now, in some sense, you have these non-commutative geometries that you can study. So there are many tools from the area of non-commutative geometry that do very interesting things. So one of the tools that I use is something called a spectral triple. And it consists essentially of a C-star algebra A, a Hilbert space H, where there is a way for me to think of this algebra A as a subalgebra of the bounded operators on this Hilbert space. And then I'll need an unbounded operator D that acts on this Hilbert space, and it's going to help me build a tool that sort of behaves like a derivative. Okay. So this is called a spectral triple. And there are a few more requirements that I need on this operator D, but I won't get into it too much here. Okay, but this is the main tool from non-commutative geometry that I borrow to study fractal sets. Okay. So the next few slides are just going to have some results on them. I won't go into too many details, but I'll just give you sort of the main ideas. So one thing one can do, for example, is use a spectral triple to define a notion of dimension. And so a notion of dimension that doesn't have to do with any sort of topological space, right? So this is one way that one can do that, right? So this is a spectral dimension that depends entirely on just the spectral triple. And so, for example, some of my results have been about this space, the Stretch-Sierpinski gasket of parameter alpha, where this alpha just refers to the length of that little interval right there. So one thing that is known about this set is that its box counting dimension is this log 3 over log 2 minus log 1 minus alpha. So it happens to be this. So this is entirely defined in terms of the space here, right? It has nothing to do with the spectral triple. But one thing that I've shown is that one can build a spectral triple so that this spectral dimension gives you this box counting dimension. Okay, so let me show you that. So this is one of the results in my my thesis. So essentially, if there's a way of building a spectral triple for the Stretch-Sierpinski gasket, so that this spectral dimension, this dimension that you can get entirely from the operator algebraic tools, it gives you this box counting dimension. And this has been done for other fractal sets. So another thing one can do is use these operator algebraic tools, this spectral triple, to define a notion of distance, so a notion of a metric, and then some notion of measure, so something that measures size, right? And so another couple of things that I did in the past was I showed that the spectral triple that I could construct for this Stretch-Sierpinski gasket, it recovers the geodesic metric on the gasket, the Stretch-Sierpinski gasket. So the geodesic metric is just looking at how long is your shortest path between 2 points in the space. And then I sort of talked a little bit about this connection between dimension and measure at the beginning of the talk here. So I told you a little bit about fractal dimension, but I didn't tell you anything about fractal measures. So one of the common ways of measuring fractal sets that we have is through using this thing called a Hausdorff measure. Okay, and so that's what you see. So for this particular theorem, I'll just direct your attention to this middle part here, this equation. So on the right-hand side here, this is entirely about the space K alpha, right? This is the Stretch-Sierpinski gasket. So this is the Hausdorff measure on the gasket, right? We're integrating with respect to this measure. I happen to have some messy constant out here, but that's not too important. So the main idea here is that on the right-hand side, I've got something defined entirely in terms of just the fractal set. But on the left-hand side, this is entirely about the spectral triple, right? So this is all operator algebraic tools. And what this shows is that integrating a function with respect to the Hausdorff measure is the same as taking that function and running it through whatever this, this tool happens to be doing. Okay, and I can talk to you a little bit about that if you'd like. But these are really just examples of how these spectral triples can be used to describe some of the tools that we have from fractal geometry. So one of the hopes that people have for these non-commutative geometry sort of tools is that they'll help us solve some problems from the area of analysis on fractals. So for something like the Sierpinski gasket, there's a way of defining a Laplacian on the Sierpinski gasket. There's a way of defining harmonic functions, and those two objects do similar things as the usual Laplacian, the usual harmonic functions. So there's a way of doing that for sets like this, and more generally for sets that are called post-critically finite sets. But the sort of trouble comes when you start talking about sets like this, where now instead of the sort of pieces for the set overlapping at just a finite set of points, now instead you have these pieces that overlap at, for example, an entire line segment here. Okay, so that overlap really causes some trouble. You can try to repeat the construction for something like this, but you don't quite get the same sort of results. So really you need to attack the problem from a different direction. And people are sort of trying different things. Some people who do a little more of the probability theory on fractal sets, they've tried attacking it from that direction. And so people are sort of actively working on this idea of how do we create something reasonable that behaves like a Laplacian, this sort of analytic tool on spaces like this, right, that have a little more overlap than something like this. Yeah. So that's some of the stuff that I've done in the past. Okay, so up next is some of the stuff that I'd like to do in the future. So this is really connections with the analysis of data, right? So with data analysis. And so I won't say too much here, but we'll say the tiniest little bit, okay? So for example, one way of connecting some of the tools from fractal geometry with analyzing data is something called Higuchi's fractal dimension. So this is an older sort of idea that was introduced by Higuchi in this paper to essentially give some way of quantifying the complexity, the sort of chaos within EEG machine data. Okay, so this, for example, is what some of the readings might look like coming from an EEG machine. So this is like the machine that they put on your head to try to measure the electric signals that are sort of at towards the top of your, the upper part of your brain, right? So near your scalp, right? So there's a way of sort of measuring that electricity, and this is what the data looks like. So one thing one can do is try to think about how would I give this some sort of fractal dimension. It seems to have some fractal properties because of this sort of repetition in the way the pattern looks. And so Higuchi introduced this idea of Higuchi's fractal dimension to try to quantify the sort of complexity within this data. And I won't quite show you how you find this dimension, but it very much relies on the fact that this is sort of time series data. Okay. So this is something people have done in the past. People have actually used this. There's a number of studies that have tried to use Higuchi's dimension to sort of differentiate between different sets of EEG machine data. Okay. So another way that fractal geometry might come in handy is in sort of complementing this area known as topological data analysis. So here I'll point you to one of the wonderful talks in this series, I think the very first one, by Dr. Jose Perea, who talked a bit about the underlying topology of data. And so one of the things that he said in that video was that topology is a branch of mathematics concerned with shapes and their spatial properties. So this area of topological data analysis really looks at a data set and tries to find the big features in it. So are there big one-dimensional holes, two-dimensional holes in it, right? What are sort of the big spatial features that exist in it? And one of the things that it maybe doesn't handle super well is what happens when there's noise in your data, right? Essentially, these tools are built to ignore some of that noise and just look at sort of the bigger shapes. And fractal geometry is ideal for looking at that noise, right? For trying to quantify that noise. So one of the things I'd like to do in the future is think about how can we complement each other, right? How can some of the tools from fractal geometry complement some of these things that are being done in this area of topological data analysis? So those are some of the things that I'd like to do in the future. So if you happen to know a lot about TDA, then I would love to talk to you about it. And I'm hoping to dive into that area a little bit more in the future. So here are some of the references for the talk. Thank you very much for watching. And I guess, I don't know, what do people say on YouTube? Like and subscribe.